Welcome to this coding problem walkthrough. In this session, we'll be tackling problem number 1454, titled Number of Students Doing Homework at a Given Time. This is a great question to practice for understanding how to work with time intervals in queries. Let's dive in and break it down step by step. In this problem, we are tasked with determining how many students are actively doing their homework at a specific point in time, which is given to us as query time. To do this, we are provided with two integer arrays, start time and end time. Each pair of values, start time, I, and end time, I, represents the time interval during which the ith student is working on their homework. These intervals are inclusive, meaning the student starts at start time, I, and stops at end time, I. The goal is to check, for each student, whether the provided query time falls within their homework interval. If it does, we count that student as actively working. Our task is to return the total number of students for whom this condition is true. The output of the problem is a single integer representing the total number of students actively doing homework at query time. For instance, consider the first example where we have start time equals 1, 2, 3, end time equals 3, 2, 7, and query time equals 4. The output in this case is 1, which means only one student is actively working at time 4. Let's break this down further to understand how we arrive at the result. In the first example, the first student works from time 1 to 3, the second student works from time 2 to 2, and the third student works from time 3 to 7. Since the query time is 4, we check whether this time falls within each of these intervals. For the first and second students, 4 is not within their intervals, but for the third student, it is. Therefore, only the third student is actively working, and the output is 1. Another example is when we have start time equals 4, end time equals 4, and query time equals 4. Here, the only student works exactly at query time, so the output is 1 once again. Now, let's look at the third example. Suppose we have start time equals 1, 1, 1, 1, end time equals 1, 3, 2, 4, and query time equals 7. In this case, we can see that all students have finished their homework by the time query time equals 7 occurs. None of the intervals include this time, so no students are actively working. As a result, the output is 0. This illustrates that the solution needs to correctly account for cases where query time does not overlap with any intervals. Additionally, the problem constraints ensure that the length of start time and end time arrays will always be equal, simplifying the input validation. The constraints further specify that the length of the start time and end time arrays will be between 1 and 100, and each interval will be within the range of 1 to 1000. The query time will also be a value between 1 and 1000. There are several edge cases to consider. For instance, all students might be working during query time, or no students might be working. Another situation is when a single student starts and ends their homework at exactly query time. Finally, for large input sizes with sparse intervals, we might need to efficiently check whether query time falls within any of the intervals. These edge cases highlight the importance of carefully handling the input data to ensure the solution is both correct and efficient. To solve this problem, we first considered a brute force approach. The idea here is straightforward: iterate through every student's start and end times, and for each student, check whether the given query time falls within their homework session. This involves verifying if the condition start time, I, equals query time equals end time, I, is true for each student. If it is, we increment a counter to keep track of how many students are working at that specific time. This method is intuitive and works well for small input sizes, as it directly addresses the problem requirements without additional complexity. Since the task involves simple comparisons for each student, the time complexity of this approach is O(n), where n is the total number of students, and the space complexity is O(1), because no extra data structures are used. Additionally, we explored an optimized approach. While the brute force solution is already linear and efficient, the goal here was to enhance the code's readability and streamline the implementation. For example, we can use Python's ability to combine the condition into a single expression, or leverage the sum function with a generator expression to simplify the code further. This optimized approach, while not improving the time complexity, focuses on reducing manual iteration and redundant calculations, making the solution more elegant and concise. This optimized approach retains the same O(n) time complexity as the brute force method because we still iterate through all the students once. However, it takes advantage of Python's concise syntax to make the code easier to read and maintain. The space complexity remains O(1), as no additional memory is required. Now, when deciding on a final strategy, the brute force approach stands out as the most natural solution because it directly addresses the problem requirements. It systematically checks the condition for each student and is robust enough to handle reasonable input sizes within the constraints of linear time complexity. However, when comparing the brute force and optimized methods, the optimized version is generally preferred in Python due to its cleaner and more concise implementation. While the two methods are functionally equivalent in terms of performance, the optimized approach eliminates manual iteration, which not only improves readability but also reduces the chances of introducing errors in larger codebases. Alternative data structures like interval trees could theoretically be applied, but they would introduce unnecessary complexity without offering any improvement in the asymptotic runtime for this problem. Since we are simply checking whether a time falls within a given range for each student, such advanced structures are not warranted here. Ultimately, the optimized approach strikes the right balance between simplicity, efficiency, and readability, making it the preferred solution. While the brute force method is perfectly adequate, the optimized version leverages Python's strengths to deliver a more streamlined implementation without sacrificing performance. The final implementation reduces the solution to a single line of code using a generator expression inside Python's sum function. This not only makes the code compact but also enhances its clarity. Here's how it looks. We define the function busyStudent, which takes the start and end times of students along with the query time. Inside the function, we use a generator to iterate through the start time and end time arrays simultaneously with the zip function, and for each pair, we check if start equals query time equals end. If the condition is true, the generator yields 1, and the sum function adds up all such values, giving us the total number of students working at the query time. This one-liner implementation captures the essence of the optimized approach: efficient, easy to read, and intuitive. In this problem, we need to determine how many students are actively doing homework at a specific query time. Each student has a homework session defined by a start time and an end time. The task is to check whether the query time falls within any of these homework intervals. To solve this, we start by understanding the inputs and outputs. The inputs include two arrays, start time and end time, which represent the start and end times of homework sessions for each student, and an integer query time, which is the time we are evaluating. The output is an integer that counts how many students have a homework session that includes the query time. To get started, we first initialize a variable count to 0. This will keep track of the number of students who meet the condition. Then, we iterate through each student's time interval using a loop and check if the query time falls between their start and end times. This is the foundational setup for our algorithm. To evaluate a student's homework session, we specifically check if the condition start time, I, equals query time equals end time, I, is true for each student I. If this condition holds, it means the student was doing homework at query time, so we increment the count variable by 1. Once we go through all the students, we return the value of count, which gives the total number of students whose homework sessions include the query time. There are a few key insights about this approach. First, a brute force solution is sufficient because we only need to check one condition for each student, which is computationally simple. With typical constraints, such as an array size of up to 10,000, iterating through the students in linear time is efficient. Additionally, since we only make a single pass through the start time and end time arrays, the algorithm is optimal for the problem. Finally, we must be mindful of edge cases, such as when no students' homework sessions overlap with the query time or when the input arrays are empty. When considering edge cases, it's important to handle scenarios like a student's start time being equal to their end time, which would mean their homework session is instantaneous. We also need to account for situations where query time does not fall within any of the given intervals or when multiple students have overlapping homework sessions that include the query time. In cases where the input arrays are empty, the output should simply be 0 because no students are doing homework. For data structures, we rely on the input array's start time and end time to represent the intervals, and we use a simple integer variable count to track the number of students meeting the condition. In terms of complexity, the algorithm operates in O(n) time since we only make one pass through the arrays. This is efficient given the constraints. The space complexity is 1, because we don't use any additional data structures beyond the counter variable. The space complexity being 1 ensures that the algorithm remains lightweight, as it only uses a single counter variable for computation. Let's go over an example to see the algorithm in action. Suppose we have the following inputs: start time equals 1, 2, 3, 4, end time equals 3, 4, 5, 6, and query time equals 4. We start by initializing count to 0. Then, we iterate through each student's homework session to check the condition. For student 0, the interval is from 1 to 3, and the condition 1 equals 4 equals 3 is false. For student 1, the interval is from 2 to 4, and the condition 2 equals 4 is true, so we increment count to 1. For student 2, the interval is from 3 to 5, and the condition 3 equals 4 equals 5 is true, so we increment count to 2. For student 3, the interval is from 4 to 6, and the condition 4 equals 6 is true, so we increment count to 3. After checking all students, the final value of count is 3. Based on the example, the output is 3, meaning 3 students were doing homework at query time equals 4. This example demonstrates how the algorithm processes each student's homework session and accurately counts the ones that include the query time. By efficiently iterating through the intervals and incrementing the counter for valid sessions, the solution achieves the desired result in optimal time complexity. The simplicity of the approach, combined with its ability to handle edge cases, ensures that it is both effective and robust for this problem. This Python implementation solves LeetCode problem number 1454, number of students doing homework at a given time. The task is to count how many students are actively doing homework at a specified query time. Each student's homework session is defined by a start and end time, and we need to check if the query time falls within these bounds. The function busyStudent takes 3 inputs: start time, a list of start times, end time, a list of end times, and query time, the specific time to check. It initializes a counter count to 0, which will keep track of the students doing homework at query time. The function then iterates through all the students using a for loop. For each student, it checks if the query time falls within their homework session using the condition start time, I, equals query time equals end time, I. If the condition is true, the counter count is incremented by 1. Finally, the function returns the total count of students doing homework at query time. This approach ensures the solution is efficient and straightforward, iterating through the input lists just once. The time complexity is n, where n is the number of students, making this solution suitable for large input sizes. This is the Java implementation of LeetCode problem number 1454, number of students doing homework at a given time. It mirrors the Python logic provided, with the same iterative approach to count students whose homework period includes the given query time. Key differences include Java's explicit type declarations for arrays and variables, and the use of a class structure. The implementation is efficient, iterating through the input arrays once and checking the condition for each student. To solve this problem, we need to determine how many students are doing homework at a specific time, called query time. We are given 3 inputs: start time, which tells us when each student starts their homework, end time, which tells us when they finish, and query time, which is the specific moment we need to evaluate. A student is considered to be doing homework at query time if their start time is less than or equal to query time, and their end time is greater than or equal to query time. For instance, if we have start time equals 1, 2, 3, end time equals 3, 2, 7, and query time equals 4, we want to check if 4 falls within the homework period of each student. This means we'll check if 4 is between the start and end times for all 3 students, and count how many of them satisfy this condition. To solve the problem step by step, we start by initializing a variable count to 0. This will keep track of the number of students doing homework at query time. Then, we iterate through each student. For the first student, their homework period is 1, 3. We check if 1 equals 4 equals 3. Since this condition is false, the count remains 0. Next, for the second student, their homework period is 2, 2, and we check whether 2 equals 4 equals 2. Again, this condition is false, so the count is still 0. Finally, for the third student, their homework period is 3, 7. Now, checking 3 equals 4 equals 7, we see that this condition is true, so we increment the count by 1. At the end of the iteration, the count is 1, which means one student was doing homework at query time. Now consider another example where query time equals 3 and all students are doing homework during this time. The inputs are start time equals 1, 2, 3, and end time equals 4, 5, 6. Again, we start by initializing count to 0. For the first student, their homework period is 1, 4, and we check if 1 equals 3 equals 4. This condition is true, so we increment the count to 1. For the second student, their homework period is 2, 5, and we check if 2 equals 3 equals 5. This is also true, so the count increases to 2. For the third student, their homework period is 3, 6, and we check if 3 equals 3 equals 6. This condition is true as well, so we increment the count to 3. After iterating through all students, the count is 3, which means all 3 students were doing homework at query time. Now let's look at a case where no students are doing homework at query time. Here, the inputs are start time equals 10, 12, 14, end time equals 11, 13, 15, and query time equals 9. Once again, we initialize count to 0. For the first student, their homework period is 10, 11. We check if 10 equals 9 equals 11. This condition is false, so the count remains 0. For the second student, their homework period is 12, 13, and we check if 12 equals 9 equals 13. This condition is also false, so the count stays at 0. Finally, for the third student, their homework period is 14, 15, and we check if 14 equals 9 equals 15. This condition is false as well, so the count remains 0. Since no students are doing homework at query time, the final count is 0. From these examples, we can see that the algorithm works by iterating through each student and checking if query time falls within their homework period. This process is efficient, as it only requires a single pass through the list of students, giving us a time complexity of O(n). The count variable is updated only when the condition start time, I, equals query time equals end time, I, is true. This ensures that the solution handles all cases correctly, including edge cases where no students are doing homework at query time. This approach is simple, clear, and guarantees accurate results for any valid input. Here, we analyze the time complexity of the solution. The main driver of the time complexity is the for loop that iterates through all the students in the start time array. Since the start time and end time arrays have the same length, which we denote as n, the loop runs exactly n times. Within each iteration, we check whether the query time falls between the start time and end time of the current student. This involves two comparisons, both of which take constant time, or O(1). If the condition is satisfied, we increment the count variable, which is also a constant time operation. Finally, returning the count value at the end is another constant time operation. Combining all of these, the time complexity of the solution is dominated by the loop, making it O(n). To summarize the total time complexity, we note that the loop runs n times, and each iteration involves constant time operations. Therefore, the overall time complexity is O(n) multiplied by O(1), which simplifies to O(n). This holds true across all scenarios. In the best case, where no students are doing homework at the query time, the loop still iterates through all n students, making the complexity O(n). In the worst case, where every student is doing homework at query time, the loop still performs the same number of iterations, so the complexity remains O(n). Similarly, in the average case, regardless of how the input is distributed, the loop iterates exactly n times. Thus, in all cases, the time complexity is consistently O(n). Now, let's examine the space complexity. The solution uses constant space, or O(1). This is because the function does not create any additional data structures that grow with the input size. The input arrays, start time and end time, as well as the integer query time, are part of the input and do not count toward the space complexity. Within the function, we use a single integer variable, count, to store the result, which requires constant space. Additionally, the loop index variable, I, is another constant space variable. Since no other memory is allocated and the space use does not depend on the size of the input, the total space complexity is O(1). Let's compare this solution to a potential brute force approach. Interestingly, the solution we've discussed is already optimal for this problem. A brute force approach would involve the same fundamental process of iterating through the students and checking the conditions, leading to the same O(n) time complexity and O(1) space complexity. However, the provided solution is more concise and avoids unnecessary coding overhead, making it efficient and clean. Mathematically, the operations scale linearly with the size of the input, as the loop runs n times and each iteration involves constant work. This reinforces the O(n) time complexity. Additionally, since we do not allocate extra memory, the space complexity remains O(1). In conclusion, with a time complexity of O(n) and a space complexity of O(1), this solution is both efficient and optimal for the problem. One of the most common mistakes when solving this problem is running into index out-of-bounds errors. This often happens when iterating through the start time and end time arrays without ensuring they have equal lengths. Accessing an index that doesn't exist will cause runtime errors, so it's important to validate the input lengths before starting your iteration. Another frequent error is misinterpreting the time intervals. Some developers assume that query time must match exactly with start time or end time, but what really matters is whether query time falls inclusively between the two. To avoid this, always use the condition start time, I, equals query time equals end time, I. Lastly, relying on a brute force approach can become inefficient for large datasets. Nested loops or redundant checks can result in high time complexity, such as O(n squared, or worse, in edge cases. To address this, optimize by using a single loop or explore options like binary search if the intervals are already sorted. Another subtle but common mistake is the off-by-one error, which occurs when inclusive bounds are not handled properly. For example, using instead of equals for the end time can lead to excluding valid intervals from your results. To fix this, carefully check your conditions to ensure the bounds are inclusive. Additionally, ignoring edge cases is a frequent oversight. Scenarios like empty arrays, a query time value that doesn't fall within any intervals, or overlapping intervals can all lead to incorrect results or crashes if not considered. To avoid this, make sure to test your solution against all possible edge cases, ensuring that it handles these situations gracefully. This problem is a classic example of interval checking, and mastering this pattern is crucial for solving it accurately. Handling time intervals inclusively is a key skill, as it ensures that all valid cases are accounted for. From an optimization perspective, if the intervals are sorted, approaches like binary search or sliding window techniques can drastically improve efficiency. These methods reduce the complexity and make your solution more scalable. During interviews, it's also important to communicate your thought process clearly. For instance, explain how you've accounted for edge cases, like empty inputs or overlapping intervals. This demonstrates your attention to detail. Be prepared for follow-up questions too, such as discussing how your solution handles larger inputs or how it adapts to heavy overlap among intervals. Finally, remember that this problem is closely related to others, like LeetCode 56, merge intervals, or LeetCode 986, interval list intersections. Reviewing these problems can help reinforce your understanding of interval-based challenges. When considering alternative approaches, an optimized linear search is a simple and effective solution. By iterating through the intervals just once and applying a straightforward condition check, you can solve the problem efficiently while maintaining O(n) complexity. However, if the intervals are sorted, binary search becomes a powerful option. Sorting the intervals by start time allows you to use binary search to quickly locate the relevant range, reducing the complexity to O(n log n) after pre-processing. For scenarios involving multiple queries, a prefix sum approach can be highly beneficial. By pre-computing a prefix sum array, you can handle range queries more efficiently. While this method requires additional pre-processing time and space, it pays off when there are numerous queries to process. Each of these approaches comes with trade-offs, so the best choice depends on the specific constraints and requirements of the problem at hand. Great job making it to the end. To wrap up, we summarized the brute force approach to solving this problem, highlighted the key concepts we learned, and discussed when to use this method. Thanks for tuning in, and I hope you enjoyed this walkthrough. Don't forget to like and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!